Okay, let's continue from our Monday's lecture. We stopped at talking about this Glivenko-Cantelli theorem. And this theorem is about the convergence of the empirical CDF function to the population CDF function. So just as a recall, we define the empirical CDF based on an IID sample with n data points, right? So this is defined as 1/n summation of this indicator function about whether each xi is less or equal than this fixed x in the domain. So what does this empirical distribution mean intuitively? It actually places a point mass of 1/n at each of this xi as its value. So that's how it looks like. So basically, if it's, let's say that I sort my x1 to xn, let's say here if d equals 1, okay? So I can easily sort them from the smallest to the largest. And this is something we call order statistics, which we will use later. But after the sorting, what does this empirical CDF looks like will be, let's say that x-axis is x, the y-axis is the empirical CDF. It goes from 0 to 1. So what it will happen is that, let's say this is my smallest, x1. So what will happen is that it will stay at 0. Once it reaches this value, it will jump to 1/n. And then once it reaches the second smallest value, it will jump to 2/n, and so on. And finally, it will reach 1. Let's say that it was there, and finally, it will be at 1. So this is 1, and this is 1 minus 1/n. So it's a step function, and it's discontinuous at every value in our sample. So it has n discontinuity points. That's the empirical CDF. But as you can imagine, right, once our n goes to infinity, we'll have very dense points here, and then the step function will have shorter and shorter steps. So it will approximate a continuous CDF. So let's say if this fx, the population CDF, defined as the probability that x is less equal than x. And here, so this x and x1 to xn, they are IID from the same f. So with this, even if this f may be continuous, but as you have the sample size goes to infinity, intuitively you can see that this empirical CDF step function will approximate this continuous f function, right? So, and the Glivenko-Cantelli theorem gives us a very strong result about the relationship between the empirical CDF and the population CDF. So by the strong law of large numbers, we already have, as we said last time, fn hat x will converge to fx for any fixed x. For any fixed x, we have this point-wise convergence. But what does Glivenko-Cantelli GC theorem tells us is we have more than this. So what this says is that if you take the soup of the absolute difference, then the soup difference will converge to 0 as n goes to infinity. And we said that we usually cannot go from here to here because this is a stronger result. But here we are able to obtain the stronger result for a very simple reason. That is, both the fn hat x and the fx are constrained between 0 and 1. So it's they're both bounded functions. So today we're going to give you the proof for this theorem. So using the boundedness, what we try to do is that, so the idea, as we have seen before, is that we are going to show the sup difference is less than, for any positive epsilon, we can show that the sup difference is less than epsilon, right? And then we can show it converges to 0 because we can make that epsilon go down to 0. So that's the idea. But given an epsilon positive, how can we show the sup difference is less than epsilon? So we are going to utilize this boundedness of the function. So we try to find integer, positive integer k with k, or I can just make it simpler. We can just find an integer such that it's greater than 1 over epsilon. So no matter how small epsilon is, I can always find such a large integer, right? So this integer will basically, I will use it to divide this interval from 0 to 1 into k plus 1 intervals. Okay, so we'll see that. Or k, 1 over k length. So basically, what I will try to do is this. Okay. So given the population CDF, so no matter how it looks like, so I'm just trying to make a very simple example. It's continuous, and then suddenly it has a jump, and maybe it's flat here, and then finally it reaches 1. So I'm just making an example. And with this k, what I'm trying to do is that I'll try to find where's 1 over k, where's 2 over k, and where is k minus 1 over k. So as I said, I'm going to divide this intervals 0 to 1 into k sub-intervals, each with length 1 over k. And then what I will do is that for each one, I'm going to find what's the corresponding value here. Okay, so let's say here it's a continuous point for f. So I can find it, and I will just call it x1. Okay, and then for k2 over k, I'll find the corresponding value. I will call that x2. Now I'm making this case where I may reach a discontinuity point. Okay, if 3 over k happens to be here in the middle, in the jump, then I'm going to call this x3. So you see the way I define my x's, and also let's say 4 over k happen to reach this flat point, flat plateau here, then I will still call that x4. I will put the minimum here as x4. So in this case, you can see my x3 and x4 just collide. So they are equal, and I allow that. So the whole idea is that I try to find x1 less or equal than x2 less or equal than xk. So let me see. Yeah, so here xk will be where my fx reaches 1. So in other words, I can just set this xk to be where my fx reaches 1. And for x0, I will have, I'll just make it clear, where fx0 is 0. So it's possible if my f has the whole real lines as domain, such as the Gaussian CDF, then it's possible that x0 may be negative infinity. I allow for that. And I also make fxk equals 1. So this xk may be positive infinity, just as the case for Gaussian, right? But for the middle ones, x1 to xk minus 1, they must be not negative infinity or positive infinity. And we know that. So in this case, with this sorted, right? So you see what I will have based on the way I define my x1, x2, and so on, right? By dividing the y interval, y-axis. So I will be able to have my xj, f xj for any j minus less or equal than j over k less or equal than fxj. So this is just thinking about this case for 3 over k, okay? So for k equals 3 in my example, because it reaches the middle of the jump. So in this case, you can see fx3 minus, this is defined as x less than xj, not equal, while fx3 is defined as the probability x less or equal than xj. So in this example, you can exactly see that 3 over k is bounded below by fx3 minus and bounded above by fx3. This is how I constructed it. And also, the way I constructed, I found the x1, x2, x3 can guarantee that, you see, because I'm dividing the y interval. So their difference, fx2 minus fx1, here is 1 over k. fx3 minus, which is here, minus fx2 is less than 1 over k, because this is a lower bound of what we have here, right? So you can naturally see that we would have, let me see, we also have fxj minus fxj minus 1, the previous points. Their difference in the y-axis is less or equal than 1 over k, right? And that's less than epsilon. This is just because of how I choose this k. Okay, so in other words, you see, I'm able to make the f value changes very small by adjacent values. And furthermore, what I have is this strong law of large numbers. I can, at every value, x1, x2, x3, I will be able to make their differences between f and hat and f very small by the strong law of large numbers, right? So by strong law of large numbers, I will have two results. That is f n hat xj minus f, or I would say, let me see. Yeah, I'm just going to use that result. It's convergent almost surely. I'm sorry, I missed the almost surely here. Yeah, and also I should have almost surely here, like that. Yeah, because the reason I need this is because this is random and this is also random. So when they have a random variable sequence convergent to a constant, we need to say the convergence mode, right? And this is almost surely. I missed that. So by the strong law of large numbers, given xj, we have f n hat xj converges almost surely to fxj. And furthermore, we can say the same for xj minus. F n hat xj minus converges almost surely to fxj minus. This is by the same argument. So if you recall, we would have, let me just explain this a little bit, right? So fn hat xj minus is the average indicator xi less than xj, right? While fxj minus is the probability x less than xj. So same, this is like an sample average. This is the population mean. So strong law of large numbers still applies here. Okay, so with these two results, you see, we are almost there. We have the fn hat convergent to f at xj for j, for all the j that go from 1 to k minus 1. Similarly, we have this for every xj minus. Then what's left is to prove the sup x for any x. So how do we do that? Here, a very nice thing we have is this k is finite because we start with a fixed epsilon. So this k is also given and finite. So this allows us to look at the differences for all of them, right? So with this, with these strong law of large numbers, since I only have finite j, right? K minus 1. I have k minus 1 here. I have k minus 1 here. So this is finite number of them. I can take the maximum of all their differences, and that will still go to 0. So I'm just going to define this quantity called big delta n, defined as the maximum of this thing. Okay, I'm going to say, maybe I'll just say this, fn hat xj minus fxj absolute difference, as well as the fn hat xj minus fxj minus absolute difference. And I let j go from 1 to k minus 1. So you see, in this max, I have 2 times k minus 1 things, 2 times k minus 1 absolute differences there. And because every one of them is converging to 0 almost surely, then together I have this converge to 0 almost surely. This is just because of this finite number. And the reason we can do this is also because we are constrained between 0 and 1. That's why we can have finite number of subintervals. All right, so with this, then let's take a look at what can we say about this quantity, any x. Now for any x, right? I can always find j. We can find j such that we have fn hat. So basically we can just have, we can find xj such that xj minus 1 is less or equal than x, less or equal than xj, right? So we can always find x somewhere there, and we can find the left one and the right one adjacent to it. And of course, this j is going from 1 to k. Okay, so given that, because both by definition, the empirical CDF fn hat and the true population CDF f, they are monotone, right? Because of this monotonicity, then we would have fn hat xj minus 1 less or equal than fn hat x, okay? And furthermore, we can have fn hat xj, here's the key, minus. The reason is that xj might be a discontinuity point, right? But still, even if it's discontinuous, let's say j equals 3, where is this discontinuous? But if my x lies between x2 and x3, the upper bound for fn hat x, or I'm pretending this is fn hat x, but it's the same. So the upper bound could be at x3 minus, not xj3, because xj3 minus is tighter upper bound of it. Okay, and similarly for f. Okay, so I have those. Then finally, if I want to find the difference between fn hat x minus fx, which is what I have here. Okay, so I want to find an upper bound for the difference and a lower bound for this difference. So you can see, to find the upper bound first, what will be the upper bound? So this minus this, to find the upper bound of it, is actually equal to this quantity minus this quantity, right? So I find the upper bound for the first one and the lower bound for the second one. When I take the difference, I get an upper bound for the difference. So this is less or equal than fn hat xj minus f xj minus 1. But what I'm still having here, you see, fn hat f, but their arguments are not matched. How do I deal with that? I need to use this. You see, I have this interesting relationship between f xj minus 1 and f xj minus. So you see, by this, I would have negative f xj minus 1 less than epsilon minus fj minus. So this is less or equal than C x minus plus epsilon minus f xj minus. Oops, I missed this. Xj minus. Here, plus epsilon minus that. So therefore, that's what I have for this side. For the other side, or for the lower bound, fn hat x minus fx. To find a lower bound, what I can do is I take the lower bound of the first term minus the upper bound of the second term. So it's fn hat xj minus 1 minus f xj minus. Again, here, the two things that don't have the same argument, I'm going to use this relationship again. You see, this one tells me minus fj minus, okay, minus fj minus, I move it to that side, is actually greater than what? Minus fj minus 1 minus epsilon. Minus fj minus 1 minus epsilon. So you see what I have here to put things together. I'm going to keep the conclusion here. So you see together, what I have is fn hat xj minus 1 minus f xj minus 1. Their arguments are matched. Minus epsilon, okay, less than fn hat x minus fx, my target. And the upper bound is fn hat xj minus f xj minus. Their arguments are matched plus epsilon. Okay, so now what if I take the absolute value for each term? So taking the absolute value, okay, by the triangular inequality, what I would have is this thing would actually be less or equal than the max, okay, of these two things. The max of the absolute value of fn hat minus f xj minus 1. First absolute difference, second absolute difference. Right? The maximum of those two plus epsilon. So we will have that. Does it make sense? And finally, you see, this is for a given x, right? So given any fixed x, we could find j to satisfy that. But now what if I take the soup of all the possible x? So even though for the soup, I may have infinite number or even uncountable many eggs in the soup, right? However, because I can always find the j somewhere between 1 and k. So therefore, you see, when I take this term, it will always be under that delta n, that big delta n. Sorry, no, yeah. So I should move it here, not to confuse you. So here. So once I take the soup, this will be less or equal than delta n, right? Among all the possible j's plus epsilon. And now we know this right-hand side is going to epsilon almost surely because the delta n is going down to 0 almost surely. Then we're done, right? Because this epsilon is any positive epsilon. We can let it go down to 0. So this hand side will go down to 0. So that's the proof. So the whole idea, just to as a recap, to emphasize the key in the proof is that we try to find a finite number of points in my domain, x1, x2 to xk minus 1. We want to find those and then try to relate the soup to the maximum of the absolute differences at those points, and that will be my delta n. So once it's finite, then it's easy, right? We can go from the pointwise convergence to that maximum convergence because it's over a finite number of possibilities. Now here, the soup, the challenge is that we have infinitely many x. Okay, does it make sense for everyone? So the key is that we have this nice conclusion. We have the soup convergence, not just pointwise convergence. So in other words, I would say this gives us the theoretical foundation for using the empirical CDF or empirical distribution in practice. And you can think about one extension of this fact. That is, in reality, right, when we want to talk about how to estimate the distribution from a sample, our first thought is to use the empirical distribution. But also later, we realized that the empirical distribution, its nature is always discrete. It has only discrete n values, while the true distribution may be continuous. Then how do we deal with that? Then we have the kernel density estimate. That's to estimate the probability density function. And that can use the kernel function to basically smooth out what we have from the sample. But that's a different story, right? How can we talk about the convergence of a kernel density estimate to the true probability density function? That itself is a different question. And we also have some nice theoretical result for that convergence, but it's not really something that's not something the same as here, but it's kind of related in the sense that we have a distribution estimated from a sample, and we have some underlying true distribution, which we don't know. All right, so empirical CDF and the population CDF. This is the stronger result about their relationship. Do we have questions before we conclude this topic? Okay, so if not, then our second topic today is the central limit theorem. So it is something we teach in undergraduate class. And here we want to give you the vector version. And also we are going to show that we can now easily prove it with the continuity theorem we talked about last week on Monday regarding the convergence law. So we are going to do that. Okay, so before we can talk about the proof of the vector form central limit theorem, I just want to talk about something I didn't mention last time, but I think it's worth mentioning so we can understand the proof more easily. So it is the mean value theorem and the Taylor theorem for a vector function or a real value, but vector domain function. So here, let's say it. So basically, we have this thing. So the mean value theorem what it says is that let's still use our F. Last time we talked about it. Let's say A maps from RD to R. Okay, and we also assume that it's gradient. So F dot, okay, now this will be a vector, right, at any X. So this F dot X, which is a d-dimensional row vector, that's what we said last time. So we assume this gradient function is continuous in this neighborhood of an xn, where the norm x minus x0 is less than r. For it's continuous in the sphere and r is positive. So we need this continuity in the neighborhood of x0. Then for any t whose norm is less than r in this neighborhood, we have this fx0 plus t. Okay, so it's still in the neighborhood r of x0 is equal to fx0 plus t times this integral. So we get, let u be a value from 0 to 1, and the gradient x0 plus ut du. So you see that when u is 0, we are just at f gradient x0. when u is 1 is f gradient x0 plus t. So it's basically the interpolation between x0 and x0 plus t. This is what we call the mean value theorem, and you must have learned this one-dimensional version of this in your calculus class. So how can we prove this? So actually the proof of this can be very short. It just requires us to define the function for this. So basically, let me just quickly do it. So let me let this h function as a function of u. Okay, u goes from 0 to 1. Defining this to be fx0 plus ut. In this definition, I consider x0 to be fixed and t to be fixed. So I just vary u. And what happened would be if I take the derivative of this h function. It just maps from 0 to 1 to real value. So when I take the derivative of this h function, you will see that I will have, by the chain rule, right? I will have the gradient of the f and then t. So I will have that. And that one thing we need to, you may wonder, this must be a scalar. Am I good? Actually, we are. The reason is because by my definition last time, this is a row vector and t itself is a column vector in d dimensions. So therefore, this is like an inner product, so it becomes a scalar. So we just need to be careful when we deal with vectors. And this is a scalar. So you see, I have what I need in here. And actually, right, so actually I should be a little more careful when I write this, because as I said, I need a scalar here. So I should write this. That's correct, because this is a row vector. After I do the integration on u, it's still a row vector, and row vector times a column vector gives me a scalar. All right, so now with this, you can see that this right-hand side, this term, you see that f dot x plus x0 plus ut du t, right? What if I move this t inside the integral? Then I would basically have it as h dot u, the integral on u, oh sorry, the derivative of h at u du. And then it's just h1 minus h0. And what is h1? fx plus t, x0 plus t. And what's h0? And that's it, right? So it's done. So that's the mean value theorem. As an extension of it, I can further go to the second derivative of f. That is, what if I apply the mean value theorem to f dot, to the gradient? Now I can go to the second derivative. And that is what we call Taylor theorem. So it's the second derivative version of the mean value theorem. So now I'm still having this f function, but I now require this continuity in the small neighborhood of x0 to be for the second derivative, not just for the first derivative. That's not enough. So let me just say that now I'm going to talk about the f dot, the two or second order derivative is continuous in that neighborhood. Okay. All right, then still for those t in the neighborhood, okay, for that t, I am going to write f x0 plus t. So if you're familiar with the Taylor expansion, it's very similar to that. It's very close to that. But the Taylor expansion is an approximation. Here we have an exact expansion. So f x0, the value at x0 plus first derivative at x0 times t. This is an inner product. For the second order term, I still need a scalar. So I will have the square term in the vector form. So that will be t transpose times t. In the middle, I'm going to get a matrix. So this t transpose is 1 by d. This is d by 1. I'm going to have a d by d matrix here. And it's going from 0 to 1, 0 to 1 for two scalars, v and u. So it's v is the one of the scalars times the second derivative. If you recall, last time we said for this f function, its second derivative called a Hessian matrix, it will be d by d. x0 plus now we have u times v times t. And then finally du dv. So double integral in the middle. Okay, so this is the proof. So the proof of this is to apply mean value theorem to this function f dot x0 plus ut. But so then once we apply it to this function, this is a vector value function from RD to RD. Once we apply the mean value theorem to that, we are able to introduce the V as another, interpolation constant, just similar to U. And that will be it. So this Taylor theorem, you see, we are going to use it for our proof of the central limit theorem, which I will state next. The reason I can do that is simply because I can express a function by expanding it at a fixed point. And the fixed point here is x0. And that will make things much easier for us because of a nice property of characteristic function. So I'm going to first review that the nice properties of the characteristic function, which we will use for proving the central limit theorem based on the continuity theorem. If you recall, the continuity theorem uses the characteristic function, right? We're going to show that as long as we have convergence in characteristic function, we have convergence in law. That's what we need for central limit theorem. And for the characteristic function itself, a nice property is that it has very interesting values at 0. So that's why when we deal with characteristic functions, it's very important that we often need this expansion at 0 so we can use its nice properties. So that's the preview of the next part we're going to talk about. All right, but for just the mean value theorem, Taylor theorem themselves, do we have questions? There are just some basics we're going to utilize. Okay. Yeah. Sorry. Oh, it's just the norm. Yeah, it's the norm in the, it's the distance. It's because we are talking about, in the d-dimensional space, right? If it's just one-dimensional space, it's just the absolute value. Yeah. Okay, so now let's talk about central limit theorem, characteristic function, those things. So for characteristic function of a random variable x at t or random vector x at t. So depending on whether x is multidimensional or one-dimensional, the t will have the same dimensions as x, right? So this is defined as expectation. And expectation is with respect to the distribution of x. Exponential imaginary unit I, t transpose x. Okay, so by this definition, something we will have very interestingly is due to the specialty about the derivatives of exponential function. So you can see that if I take the derivative here, this will become d-dimensional first of all. And then what will be it? You see that, so once I take the derivative against t, I'm just doing it for now. So you see that this exponential will stay by the property of its derivative. And by the chain rule, I am going to have the I and x come down, right? And also, because our definition that it's row vector and x itself is column vector by default, I need to be a little careful here. So I will come down, but x I need to write as a transpose so that it's a row vector. Okay, so with this, then you see what happens if I set t equals to 0. When I set t equals to 0, and this is a 0 vector, okay? What happens is that I'm going to have like exponential 0. That's 1. And imaginary unit here, I can come out expectation of x. And the transpose can come out as well. So you see, I'm having this moment of x, first moment of x. And it's related to, the first moment of x is actually related to the first derivative of the characteristic function at 0. So this is a nice property of the characteristic function. And also, you know, something related to the characteristic function is what we call the moment generating function. So for that, we are going to be able to generate moments by taking derivative of the moment generating function. But the characteristic function is more general for many reasons. So here we talk about that instead of the moment generating functions. Now you can see the moment property still, we have some interesting properties for the characteristic function. All right, how about second derivative? Okay, second derivative is going to be a matrix, d by d matrix. So you see, if I take derivative for t again, because these two things don't involve t, t is only in the exponential term. So we will have another I and x come down. And exponential still stays as exponential by the chain rule. Okay, we would have I squared, and that's equal to -1. How about x? We have another copy of x coming down. But one thing we need to note is that here we need to have a d by d matrix for the second derivative. So this is 1 by d. We would have x times x transpose, and that will give me the d by d. So you see, this is -1. And if we let t to be 0, first exponential term will become 1 again. This is -1. So I will actually have negative, you see, exponential x times x transpose. This is what? Second moment, right? This is the second moment of x. And you see, we can actually have it by letting the second derivative of the characteristic function evaluate as 0. So these are the two nice properties we are going to utilize in our proof for the central limit theorem. And we'll state that for now. So this is the vector form central limit theorem, short as CLT. Maybe you have learned the scalar form, but now we're going to talk about the vector form. So let's say that we have x1 to xn, okay? And they are IID following the same distribution, independent, with the mean vector with, for each xi, its mean is mu. This is d-dimensional, and we write the variance notation But because it's d-dimensional, this is a d by d covariance matrix. We call that sigma. Okay, this is d by d. And also, to allow this CLT to happen, to hold, we need this mu to be finite in its every element, and this sigma to be finite in its every entry. Okay, and also just for your information, the definition of the sigma, if we write it out, it can be written as the expectation of xi minus mu times xi minus mu transpose. Again, this is a d by 1 by d, right? So that gives us a d by d covariance matrix. Okay, so our basic condition is this finite variance and IID. With those two simple conditions, and regardless of the distribution of xi, right? It could be Gaussian, but it could not be. So the nice thing about central limit theorem is that as long as your n goes to infinity, then the average of their x1 to xn, subject to centering and scaling, will be normally distributed, d-dimension Gaussian. And that's very nice result. So this is the foundation for establishing the importance of Gaussian distribution, because we have a lot of the, in reality, a lot of our measurements are some sort of average, even though we may not realize that. But so this is saying that averaging things have nice Gaussian distribution. So this can explain why we see a lot of data have Gaussian-like distribution. And I think the foundation is central limit theorem. So what's the conclusion here? Given the condition, then this is something we will see a lot of times in this class. Root n times xn bar minus mu. This is what I mean by centering. This is what I mean by scaling, times the square root of the sample size, will converge in law to a d-dimensional Gaussian distribution with mean zero covariance matrix sigma. So if you recall in the first lecture, I briefly mentioned this, and also I said, why don't we have n on this right-hand side? The reason somebody answered this question saying because on the right-hand side it's a limit, right? When n goes to infinity. So we shouldn't have n on the right-hand side. Everything related to n should stay on the left-hand side. Okay, so this is the multivariate version, vector form. Yeah. Oh, sorry. Yeah, thank you. Yeah, it should be this, like that. Yeah, because we already subtracted mean on the left-hand side. Okay, so how can we prove it, right? We want to use the Levy's continuity theorem. So to do that, we need to get a characteristic function for this and the characteristic function for that. And we're going to show that this characteristic function is convergent to this characteristic function. That's the idea. So to first, maybe I will leave this Taylor's theorem result because we're going to use it. I'll erase other parts. Okay, so to prove it, the central limit theorem. So the first thing, what I need is to get a characteristic function for the left-hand side. I will write as this phi root n xm bar minus mu at t. Okay, so thinking about the definition of the characteristic function, it is exponential I t transpose times the random vector we work with. Right. And then don't forget, what is my xn bar? we know that, this root n, xn bar minus mu. If we write out the definition of xn bar, it is 1 over n summation xi minus mu, right? And furthermore, I can write it as, you see, for this summation, I can further write it as xi minus mu. Put mu in the sum, because here I will have minus n mu divided by n. It's the same. So the way I write it this way is because I want to have some cancellation here. So it's basically 1 over root n. Okay, with this, let me put it inside and see what I would have. It stayed 1 over n, 1 over root n summation. Okay, and because we know summation in the power is equal to product, right? So we can actually write this as the product, right? Exponential. And I have this exchange of the product and expectation. IT transpose what? 1 over root n xi minus mu. And now the IID thing will come into play because x1, x2 to xn are IIDs, which means that this term will have the same expectation regardless of I. So therefore, I can write it as the nth power of expectation. IT transpose 1 over n. I'll just write x1. x1 minus mu. Okay. And also, just this may be something simple, but I want to make a clarification that we have 2 i's, right? One for the index of the sample data points, one for the imaginary units. Just be careful that they're different. So now you see, what is this term? If I combine t with this 1 over root n, in other words, I can write it as t divided by root n transpose, right? T is a vector, root n is a constant. Well, this is actually the characteristic function of x1 minus mu at t over root n. This is the definition, to the power n. So in other words, the left-hand side's characteristic function can be expressed in this. I just need to derive the characteristic function for x1 minus mu, the centered version of my data, of my random variable. Okay, so now for the inside, because one thing we can actually know is that this n is going to go to infinity. It's going to infinity. So this term t over root n is a very small constant, or it's a very small vector. It's a very small vector in terms of norm in the RD. And in fact, you see, connecting it to what I have in the Taylor theorem, and also we know characteristic function has a nice property at 0. One thing I forgot to say is that for the characteristic function itself, if I just have it as at 0, evaluate at 0, I would always get 1 by definition. So we know characteristic function has a nice property for itself as 0, for its first derivative as 0, for its second derivative as 0. So we're going to use those and to approximate or to expand this by the Taylor theorem. All right, so let's see. So what is the, I'm going to do the expansion here. Okay, Taylor. Phi x1 minus mu at 0. That's what I have first. Plus first derivative x1 minus mu at 0 times, what do we have here is t. Here is t over root n. Second order term, it will be t over root n transpose times second derivative in the double integral. Okay, v times phi x1 minus mu, second derivative, x0 is 0 in my case, u v t divided by root n du dv times t over root n. Okay, and finally, I will conclude this raised to power n. So this is what Taylor's theorem tells us. Now I'm going to erase this part and simplify what we have. So by the properties I wrote on the left-hand side, on the left, so when we evaluate this characteristic function at 0, it's 1. Second, you know, this, based on what we have, is I times expectation, okay? And the expectation of x1 minus mu is 0 because mu is its mean. So I will have 0 for the second term. Now I'm left with the third term, t over root n transpose. So inside this, what do I have? I would have everything with me. So you see, this is the v will stay, this will stay, and dv du will stay, and that, right? So, but what I can simplify is that I can combine the root n and root n over there. So the third term, I'm going to combine it as 1 over n t transpose double integral for uv okay, uv t over root n t. Okay, raised to the power n. All right, what happens when I let n go to infinity? For this term, it's 1 plus something divided by n. And this something, this is a scalar, by the way. You see, what happens when I let n go to infinity here? Because u and v are both between 0 and 1. And also this t is just in Rd, fixed t, right? A fixed vector in Rd. When I let n go to infinity, this would actually converge to 0. So therefore, you see, I would have pointwise convergence for this whole term here to the second derivative at 0. And that would be my, so I forgot what I have here, right? That would be this. So you see, I'm going to write it here. So when I let n go to infinity, x1 minus mu, uvt over root n. Okay, when I let n go to infinity, this will converge to x1 minus mu, second derivative at 0. And by what I have over there, it will be equal to negative expectation x1 minus mu times x1 minus mu transpose. And this is the definition of covariance matrix. So you see, I would have that. right? So this will be the limit for this part. And this will go to n go to infinity, 1 over n. So another thing, and also to the power n. Another thing I want to say is this, right? So this is a calculus result. So if we have 1 plus some constant a divided by m raised to the power n, what we know is that this thing, as n goes to infinity, will be, or I shouldn't say this. So this is actually in the same order as, actually, yeah, n goes to infinity. That's right. When I let n go to infinity, this will converge to exponential a. So that's a result we will also use again and again in later lectures. So when we let n go to infinity. So with this and with what we have here, you see, this term will basically converge to our a. And the limit of this is negative covariance, or negative, sorry, T transpose times negative covariance matrix times T. That becomes a scalar. And we have n here, we have the power here. So altogether, when we let n go to infinity, we are going to have it converge to exponential to the negative T transpose sigma covariance matrix T. That's it. And also, I think I forgot one thing somewhere is the 1/2. Let me see where I missed that part. Let me see. Is that, oh yeah, that's my, sorry, my bad. That's right, the interval. The interval here, right, I only said like that. I only said this converges to that, right? So this only about this part, but I missed the interval. So the interval here, you know, this is double interval, integral v, right? And I have this du dv, which I missed. Right, and that, you see, together, the integration, once I move this term out to the negative sigma, that will give me 1/2. Okay, so now the limit for the characteristic function of this thing turns out to be the characteristic function of the d-dimensional Gaussian with mean 0 and covariance matrix sigma at t. Right, and we're done. That's the central limit theorem proof. So we just directly apply the Levy's continuity theorem to show the convergence of the characteristic function. And that will give us the equivalence to the convergence in law. And during that, we use a lot of the asymptotic properties, primarily the Taylor expansion, right? That's not asymptotic, but we use that expansion. And also we have this result, which we'll use a lot later. And also the properties of characteristic functions and its derivatives at 0. Okay, so do we have questions for central limit theorem? And for the condition when it applies, as a reminder, IID and finite covariance for each xi. Okay, so I think this is what we have. This is an extension of what we learned in the undergraduate class, right? We learned the one-dimensional version for central limit theorem. Now it's the vector form. So next, what we will talk about is even more general than the central limit theorem, where we will keep independence of our random variables in the sample, but we will drop the identical distribution. So this will be the more general form of central limit theorem. And sometimes you will see people refer to this as the Lindbergh or Lindbergh-Feller central limit theorem. So it's a more general form. So compared to the IID, classic central limit theorem, the Lindbergh-Feller version drops the identical distribution, but only keeps the independence. Okay, so this is for independence, but not identically distributed. And this is more common in practice. We will actually encounter some statistics formed in this way. Let me just give you an example as a motivation. And just for the time constraint today, we're going to give you the statement and we're going to prove it next time. Okay, as an example, think about this. Let's say that you have x1 to xn IID, no problem. But what if you are going to have a constant modified to the term, right? To modify the term. So what if you define some statistic Zn as the summation I from 1 to m of some constant lowercase ni times each xi minus mu. So these xi are IID with mean mu, right? Mu is still the mean. So I'm still doing a centering, but when I take the sum, I'm not directly taking the sum. I multiply by some constants. So Zn1 to Znn are constants. Constants. So then the question is, under what condition of Zn1 to Znn would this statistics Zn subject to some scaling, okay? Because it's centered already, but subject to some scaling, still converges in distribution to normality, subject to some scaling. So that's the question we want to answer. We want to expand what we have under the classic central limit theorem. It's not, we don't want to be constrained under the sample average, right? This is a special case. But what if we want to add something here for weights, and then the weighted statistic will still satisfy the asymptotic normality? That's the question we're going to address under the Lindbergh-Feller theorem. So just in general, think about what we have as the sample size goes to infinity. So the general case can be written as a triangular form. So what I mean is that, let's say, here is the sample size. Okay, so when it's 1, I have only one random variable and then write as x11. So 1 for the sample size, 1 for the index in the sequence. 2, I have x21, x22. So 2 random variables and my sample size is 2. When I have n, sample size goes to, when I have sample size n, I have xn1, xn2, 2xnn. So you see, this is a triangle because given a sample size, I will always have that number of random variables and so on. So when we talk about asymptotics, we actually let the sample size goes to infinity and we wonder what the average of the sequence would be, right? So you see here, once I take the average, I will call this x1 bar, I will call this x2 bar, and this xn bar, and so on. So under the special case, you see, I may have x21 equals x11, xn1 equals x11. So that means whenever I increase the sample size, I keep my random variables by just adding an additional one, right? So I increase the sample size by 1, by 1, by 1. But that's just a special case. Here, I'm just saying that I can let the sequence given sample size to be with n random variables, and these can be not related to the previous sample size, and that's okay. And under the theorem, what we would just require is that all these things are independent. So the Lindbergh central limit theorem says for any n, for any sample size, xn1 to xnn, the n random variables are independent. Independence is required, but not necessarily identically distributed. So for simplicity, I'm just going to assume every random variable here is centered. I just subtract its means. I don't need to worry about its mean, but it's just, I can do this without loss of generality because we can always do subtraction of mean. So I would say without loss of generality, we assume this every random variable has mean 0. That will make the derivation simpler. But for the variance, I allow them to be different. So they can have their own sigma ni square as the variance. And also, I'm making things simpler for the Lindbergh theorem, central limit theorem, by saying we are talking about one-dimensional things. So here, the multi-vector form is not really what we use here because it will make things a little complicated, but we are just talking about one-dimensional thing. So with this different variance, and then what this theorem says, I'll just write it down and then we'll conclude. We'll stop here. So what this theorem says is that under what we call the Lindbergh condition, we can still have asymptotic normality. Okay, so I will just denote the summation of the n random variables at Zn. Okay, so sample size is always denoted for clarity. I will also denote the sum of their variances by Bn squared. The reason is that they're independent, right? So this Bn is just equal to the variance of Zn. And I have the Bn squared, so I don't need to write Bn square root. I can just write Bn. So then under the Lindbergh condition, which I will say in a minute, we would have a very nice result. Zn divided by Bn, not Bn squared, but Bn will converge in law. Convergent distribution in law, the same thing, because here we're under one-dimensional Gaussian standard normal. So yes, we're saying that Zn divided by the square root of its own variance, right? It's the standardized version of Zn will converge in law to standard normal. And that's a very nice result. But what's the Lindbergh condition? It's actually written in this way. Bn squared for any. So the condition is stated as in this way. For any positive epsilon, we consider epsilon times Bn. Bn is the standard deviation of Zn. And for every x and I, the random variable, we compare its absolute value to epsilon times the standard deviation of the sum. And you see, so one way to interpret this is that when epsilon is super small, then we will have indicator function taking value 1 for every I. Simply assume that we have every value taken that for the I. And then indicator becomes 1. And the summation of x and I squared is what? Is actually Bn squared. And that will be what? Then summation of this becomes summation, and x and I squared will be sigma, what I want to say is this. So this is something we have by the condition. Then you have bn squared divided by bn squared. It's 1. That will not happen. So because then that's not allowed because 1 is not going to 0. But this Lindbergh condition says that for any epsilon positive, no matter how small it is, we must have this going to 0. So you can think about this, think what it means, right? Before we come back to the next class. But actually has a very strong condition on how the random variables xn1 to xnn would behave. So intuitively, you can think about this condition meaning that we won't have one of the n random variable that really dominates the variance. So they contribute almost equally in some way. So that means we have this averaging, the average behaving like normality. So in the classic central limit theorem, we don't need to worry about this because they all share the same variance. So that means their contribution to this total variance will be equal for sure. But once we have this different variance allowed for the n random variables, it's possible that one of them may dominate the variance, but that's not something we want. Okay, so we will stop here and we'll come back to this Lindbergh theorem next time.